Okay, so we're doing section 8.13, which is VSEPR theory. And VSEPR theory stands for valence shell, electron pair, repulsion theory. And so the whole idea of VSEPR theory is we're going to be looking at molecules from that localized electron bonding model, where we consider all of the bonding electrons to be shared between the bonded atoms directly between the two nuclei. And when we say the valence shell, when we say valence shell, we're talking about the electrons in the valence shell. Okay, we're talking about electron pairs. And so something about this, I actually would, this has sort of been around for a while, but the electron pair part of this, I usually kind of think of it more as an electron group. Okay, but electron pair is sort of what you think about as far as a bond. A bond is occurring where you have overlap of two orbitals and you share a pair of electrons. But we'll talk about how we have these electron groups, which are sort of a better way of describing what we consider electron pairs, and repulsion. So the idea is we have electrons in bonds and lone pair electrons that are going to repel each other. And what this allows us to do is actually predict the shapes of molecules, okay? And that's important because when you have the opportunity to predict shapes, that has implications for chemical reactions and how molecules might, say, bind inside of a protein or the like. Understanding the shapes of things and how they fit together is important for the chemistry that goes on in the real world. And so this is a really important part of being able to understand the chemistry that goes on, say, especially if you're like going into something in medicine or biology, understanding how the molecules interact with each other, right? It comes out of these shapes. Or something else that if you go on to organic chemistry, they call it sterics, basically the size of and shapes of molecules. And so in order to get started down this path, we have a few things we need to define. And one of those, here's kind of a list of those things. One of them being the steric number, okay? The steric number is for a central atom. And so all we're talking about with a steric number is the number of lone pairs plus the number of bonded atoms. So I've got a molecule down in the bottom right to illustrate a few of these things. You know, on this molecule we have, we can look at the carbon as being the central atom, but we can also look at the oxygen as being the central atom, a different central atom as well. Because you can take central atoms one at a time, especially if you have large molecules. And so for the carbon is bonded to 2 hydrogens and 1 oxygen for a total of 3 bonded atoms, and it doesn't have any lone pairs. Therefore, the steric number of this carbon would be 3. For the oxygen, you can look at the oxygen as being its own central atom, and it would be bonded to a carbon, and it would have 2 lone pairs of electrons, so it would have a steric number of 3 as well. And that's going to be something that's going to be useful for us as we start to determine the VSEPR class. Okay. Now the VSEPR class is just a designation for how we can or sort of organize the different types of molecules that are out there. And we do that by labeling the atoms in certain ways. Now, most of the atoms that we're going to deal with, or excuse me, most of the molecules that we're going to deal with are going to have one central atom, at least until we get more familiar with the different shapes that we will encounter. So the first central thing we'll look at is A, which is our central atom. We'll have X, which is atoms that are bonded to that central atom, and E's, which are lone pairs. So in our example over here, we can think of our carbon as being the central atom, and so that would be our A. And then there are 3 bonded atoms, so it would be X3 with no E's around that carbon, okay? And so that would be our VSEPR class for that molecule, assuming we're just looking at the carbon atom as our central atom, okay? Now, these VSEPR class, these designations will lead to a couple of things. One of them is the electron geometry or electron shape. And the key here, when I say geometry or shape, it's going to be relating the electrons to each other in the electron geometry and electron shape, okay? And so what this does is it's going to describe how electron groups are ordered around that central atom. Now, I've got some, so the images we'll be looking at are going to be, two artist renderings, right? These artist renderings, obviously, they're two-dimensional, right? They're in the plane of the page or the paper, that's the screen that we're looking at, but they're representing things that are in 3 dimensions. And so there are going to be some things that you're going to need to start to think about more spatially than a lot of the stuff we've done in the past, especially when we get to things that molecules that take up 3-dimensional space, as opposed to we can draw them out in 2 dimensions really easily, okay? And so these shapes are going to be things that you're going to have to learn and apply. Now, unfortunately, we're not in the classroom. This is one of those times where I like to give you some more resources to look at these shapes, but we're really limited in this particular type of an environment. So hopefully the 2-dimensional pictures, these artist renderings, are going to be good enough to help you see in your head. And that's the key. Seeing these things in your head is going to be of utmost importance for understanding their shapes. Okay. So when we look at the electron groups and the electron geometry is going to be dependent upon how groups of electrons repel each other. Okay. So among the different types of electron groups, there are really 4 things that we're going to consider. A lone pair of electrons is going to be considered one electron group, and a single bond is going to be considered an electron group. And even though a double bond has 2 pairs of electrons that are being shared, we're still going to consider it one group. And the same goes for a triple bond, which would be 3 shared pairs of electrons. It's still also going to be considered just one group of electrons. And now there's reasons for this that we won't get into yet, but we will get into a little bit later down the road when we're in, say, chapter 9, and we start understanding how the orbitals overlap for given double and triple bonds, and how certain orientations of the orbitals and how they overlap between 2 bonded atoms will have little influence on the overall shape of the molecule and the electron geometry and electron shape. So once we have an electron shape or electron molecule, and the key here is, remember, with electron shapes and electron geometries, we're talking about the electron groups. When we talk about the molecule geometry or the molecule shape also, or molecular geometry or molecular shape, right? We're talking about a description of how the surrounding atoms, right, are ordered around that central atom. So when it comes to electron geometry, it's how the electron groups are ordered. When it comes to molecule geometry, it's how the atoms are ordered. So when it comes to a molecule geometry or molecule shape, we aren't going to factor in the where those lone pairs of electrons are. We're only going to factor in where the atoms are. Now, those lone pairs of electrons, because of the electron geometry, they're going to influence where the atoms are around that central atom, but we're not going to include those when we describe the shape of that molecule. And this will become more apparent as we go. Another thing we're going to look at is the bond angle. So the bond angle is really just the angle between any 2 bonds, okay? So if we look at the angle between, say, this bond here and the double bond here, that's about 122 degrees in this molecule, which is a formaldehyde molecule. Whereas the bond angle between the hydrogen bonds here, right, that's going to be 116 degrees. And so that bond angle is going to be something that's also influenced by where those electrons are. And we're going to see how the bond angles will be influenced by electrons, but also size of atoms as we proceed through understanding of molecule shapes. Yes, Maya.
Yeah, I just wanted to go back to when you said water was bent. What was the angle of water again?
So water is about 104 degrees. And so we'll talk about why that is when we get to water's group. But we're gonna find that there are going to be some ideal bond angles and there are going to be some actual bond angles. And I'm not going to have you memorize any of the actual bond angles because those are specific to a certain compound. What we want to do is we'll look at the ideal bond angles and how those might differ from for certain molecules compared to others. But yeah, water is about, so it's for us, what I would expect you to know for water, its bond angle is less than 109.5 degrees, which is something we'll talk about when we get to a particular electron geometry called the tetrahedral geometry. Okay, so there are some shapes of molecules that we're going to encounter. These are all listed here. The various shapes, and actually there's more than just this, but we'll see those as we go. These are some of the common ones that we'll see. These molecules that we're going to see, we'll do some representative examples of the molecules and we'll draw them out. And I want to remind you when it comes to drawing, some things we talked about earlier in chapter 8, which are using perspective drawing. Okay, so with perspective drawing, what's going to be really important is when we have, so if we have a molecule that is T-shaped, right? T-shaped is going to be a molecule that has all of the atoms would lie in the same plane, right? So in this case, the plane of the screen that we're looking at, all of the atoms would lie in that plane. A trigonal planar molecule, well, it's planar. It's actually in the name. All of the atoms would lie in the plane of that molecule. Square planar, all of those atoms would lie in that square, in the plane, the same plane, right? Linear molecules would be the same case. They're all going to lie in the same plane. In fact, they're going to all lie on the same line if we have something linear. We'll get to that. But when we start to get shapes that are three-dimensional, trigonal pyramidal, trigonal bipyramidal, square pyramidal, octahedral, tetrahedral is another, right? Those are all going to be three-dimensional molecules that we're representing in 2 dimensions. And so we're going to use perspective drawing to illustrate that. And so if I have a tetrahedral molecule, right? If we have something that's tetrahedral, we're going to have, again, I'm going to try to draw this out. Here's my A, that's my central atom, X and X. This is a central atom that's bonded to 4 things, and we'll talk more about this in a little bit, but I want to reintroduce and make sure you remember the things that we talked about earlier, right? And that is the lines. Okay, so when we have a line, okay, that's a bond in the plane of the board, the page, whatever you're looking at it. Right, screen, page, right? If you have a wedge, and this wedge should always be filled in. Okay, so the wedge is a bond that projects out toward you. Right, that projects out of the plane of the page. Toward you. Right, so that atom, this atom X, that is closer to you, right? So X here is closer than A. Right, so this X right here is closer than A. Okay. And the other one that we have is this dashed line. Okay, and so the dashed line is a bond that projects back away from you. Right, so you could say into the plane of the page or into the board. So actually the key here is when we look at this X, that X is farther away than A. Okay, and those are things we're going to come back to kind of over and over again because we're going to start to get to molecules that have shapes that aren't linear. Okay, and so keep that in mind, and you're going to need to learn how to draw out molecules using that in order to show the shape without, and the nice thing about this, a wedge showing that, a dashed line showing that, is that it means that we can draw out these three-dimensional things on a two-dimensional page without being a very good artist, which is good for me. I hope it's going to be good for you. Okay, so here is another sort of a set of examples of how these molecules will have shapes or electron geometries. You'll see if we think about the central atom versus surrounding atoms, okay, we're going to have the central atom will be right in the middle, and we're going to consider the surrounding atoms, if you will. You can sort of put the surrounding atoms on the sphere of a surface and start to see how those the bonds are oriented. For example, if you have a linear molecule, you'll have this bond angle of about, well, it'll be 180 degrees as far as a bond angle goes. And so these bond angles are going to be things that you see. And so over on the right, we have bond angles that are associated with the various shapes that we'll have, and in particular the electron geometries. So these are what we're going to call our ideal bond angles. Okay, and so if we have a linear molecule, there's going to be an ideal bond angle of 120 or of 180 degrees. If we have a trigonal planar molecule, we're going to have an ideal bond angle of 120 degrees. Essentially, you'll have a central atom in the middle and three surrounding atoms. With the 180 degree, that linear bond angle, you'll have a central atom in the middle and only two electron groups, so two bonded atoms. When you look at the tetrahedral molecule, so what we have there is we have, see if I can draw in my wedges and dashes to help illustrate that, right? This atom here is coming out of the plane of the board at you, and this one's going back at you, or back away from you in the back there. And so that will give you a bond angle of 109.5 degrees. So when you think about the orientation of the bonds in a tetrahedral shape, essentially you'd have the central atom and these four surrounding atoms that are spaced as far away from each other as they can possibly get on a sphere. And without going into all the math of it, what you need to know, and this is sort of the one weird bond angle, is this 109.5 degree bond angle as the ideal bond angle for something tetrahedral. When we get into trigonal pyramidal structures, we're going to have a couple of different bond angles that we'll look at. One type of bond angle is going to be a 90-degree bond angle, and that's going to be between a couple of different types of atoms. So, and we'll talk more about this in the future, but the top and bottom atoms in this particular rendering of the molecule are what are called axial atoms, right? Just like the axis of the Earth, kind of, you know, the axis that the Earth spins on, or it gives you a straight line. And then you have the 120-degree angle, so that those axial atoms will form a 90-degree angle with all three of the atoms, you know, one at a time, around the central, or the equator of the molecule. Those ones around the middle are going to be called equatorial atoms, or they're at equatorial positions. And so the angle between an axial atom and an equatorial atom is 90 degrees, whereas if you have neighboring equatorial atoms, those are going to be 120 degrees as their ideal bond angles. And that's for a type of shape that we call trigonal bipyramidal. And so we'll get to some of those in a little bit. If you have an octahedral shape, all of the bond angles are going to be 90 degrees. There isn't actually an equatorial or axial. It's just they're all 90 degrees from each other because you have six atoms surrounding the central atom. So in that case, you'll have bond angles of all 90 degrees. And so these are going to be some of the shapes and bond angles that we're going to see as we construct our VSEPR theory. So here we have, again, some of those representations. Again, these are artist renderings. And on the left, there's a table of the molecular shapes that we will see. Now, the molecule shapes are going to be related to electron geometries. If we come back up here in this slide up here, we have a bunch of electron geometry. These are how the electron groups are spaced out with respect to each other. If we go to the next slide, this is where we're going to start to differentiate between electron groups and how those can be either atoms or lone pairs. We're going to actually differentiate between the lone pairs and the atoms. And so we're going to find that when we have atoms that are, so if we have, for example, all of the electron groups are accounted for as atoms, for example, something like AX3 where there are no lone pairs, that's going to give us something, if they're all the same type of surrounding atom, it's going to give us something that has the ideal bond angles. But if we replace one of those atoms with something that has a lone pair of electrons, right? So a lone pair of electrons is represented by these green lobes, essentially showing, hey, there's electrons there taking up that space. That's going to give us something that has a slightly different shape because the lone pair isn't part of the molecule shape. So even though these two examples have the same steric number, right? Those are both steric number 3. Right? Even though those both have steric number 3, one of them is going to be trigonal planar and the other one is going to be bent. And so we're going to be able to take into account when we have atoms versus when we have atoms and lone pairs. And so that'll come into play as we start to put these classes together. And the figure on the right kind of shows you, based on the same type of a representation we saw in the previous slide, where all of the atoms or all of the electron groups are accounted for as atoms. Here now we're going to start to look at what happens when we remove those atoms, one atom at a time. And so we're going to have these different classes of VSEPR structures. And so again, this table on the right is organized by, first off, steric number. Okay. Then based on how many lone pairs there are. Okay, so that's going to be something we'll explore as we put in, as we start to do these molecules. Okay. So we're going to start out with the simplest of molecules, which is AX2 molecules, and something we can do, and we may come back to this occasionally to look up examples. There are a few examples of AX2 molecules. There's, so BeCl2 is what we'll start with, but we'll also think about carbon dioxide in here. So we'll do a couple of examples, but we have examples of these types of molecules throughout. Okay. So if we think about an AX2 molecule, we're talking about something like BeCl2. Now, the key here for understanding how to determine it's an AX2 molecule is we have to draw the Lewis structure, okay? The Lewis structure, though, does not tell us shape. What the Lewis structure allows us to do, right? It lets you figure out the structure or the VSEPR class. But it's technically not showing you the shape. When I say it's not showing the shape, you can draw all kinds of Lewis structures that don't show how the atoms are oriented with respect to each other. And you can learn some things about that. The things that you learn about that are going to be the things that you need to determine the shape and determine how to draw the molecule using perspective drawing. Okay. Okay. So we'll start out with the BeCl2 molecule. So BeCl2. First off, again, we're going to draw Lewis structure so we know how to do it. So beryllium has 2 valence electrons. Chlorine we have 2 of them, and they each have 7 valence electrons. So we have a total of 16 valence electrons. So here's our beryllium in the middle, chlorine, chlorine, right? We draw our bonds, we subtract off the bonding electrons, and we get a lot more practice with this starting tomorrow in lab when we do, when you have the Lewis structure lab. So you've got 12 valence electrons remaining. We start placing them as lone pairs around the more electronegative element, which in this case is chlorine. And so we say 1, 2, 3, 4, 5, 6 lone pair electrons around chlorine. So we get to its octet. 1, 2, 3, 4, 5, 6. That takes care of the 12 valence electrons. Remember, it's okay that beryllium has it doesn't have a full octet because it's in period 2, and it's one of our exceptions to the octet rule. And so here, this particular molecule shows that we have 2 bonded atoms, right? A chlorine atom and a chlorine atom bonded to the central atom. So if we were to draw out so if this is the Lewis structure, if we draw out the perspective drawing, really when you have the perspective drawing, you don't actually need to draw in all of the lone pairs. Sometimes it's useful to do so, but here we don't really need to, because what we're doing is really just showing how the atoms are oriented with respect to each other. And so one of the things I'm gonna pop in here is that angle between those 2 bonds, right? So the beryllium chlorine bond on one side and the beryllium chlorine bond on the other side, that's gonna be 180 degrees. Okay, and so that is gonna have a shape that is linear. Okay. We'll do this now for another molecule. So we'll also do it for carbon dioxide. So if you actually do the carbon dioxide Lewis structure, you've got carbon, which has 4 valence electrons. You got oxygen that has 6, but there are 2 of them. So you have a total of, again, 16 valence electrons. We put our carbon in the middle and our oxygens around it. We put in our single bonds, leaves us with 12 valence electrons left to place, and we start to place them again. So 6 around the first oxygen, 6 around the second oxygen, because the oxygen is more electronegative. And we've used up all of our valence electrons. So what we have to do now is we have to go and adjust this, right? And so we have to do that because carbon is not one of the exceptions to the octet rule. So we're going to take this lone pair of electrons here, move it to form a double bond. We'll take this pair of electrons here, move it to form a double bond. We'll get our CO2 molecule. And this is going to be the Lewis structure for the CO2 molecule. Okay, so that's our Lewis structure. Okay, now when we're doing the perspective drawing for this, when we do the perspective drawing, we should still draw in the double bonds. I think it's really useful to make sure we do that as often as we possibly can. So we can draw in the double bonds. We don't really need to put in the lone pairs of electrons, because our really important piece here is that we can now say, okay, the angle between those 2 bonds is going to be 180 degrees. So this is also going to be linear. Now, the reason why these are going to be 180 degrees is, well, what you have in the bond is 2 lone pairs of, or 2 shared pairs of electrons, or in the case of CO2, a bunch of shared pairs of electrons. But in particular, what you're seeing is pairs of electrons that repel each other. But those pairs of electrons are still connected to a central point. So how do things get as far away from each other as possible if they're connected to a central point? Well, if you think about it, if I have, so my pen's here to represent the bonds, the way those bonds, those electrons get as far away from each other as possible is if they're directly opposite each other on that central atom, that central point. Right? Let's see if I can right? So if they're directly opposite each other, that leads to a bond angle of 180 degrees. And if you have some things that are 180 degrees apart, it's going to give you something that is overall, right, linear. Okay, so that's our first class of molecules in VSEPR theory. Now, there's only one set of molecules that are AX2, right? They're always going to be linear molecules. When we get to steric number 3, we're going to have two types. We're going to have AX3 and AX2E. So if we go back up to the shape here, right, this is the one that we talked about before. So when we look at the AX3 versus AX2E, again, we're going to be able to figure this out doing Lewis structures. And so we'll pull in a couple of examples of each of these, but the whole idea is you have 3 surrounding atoms for AX3 and 2 surrounding atoms and 1 lone pair of electrons for AX2. And so let's put down, let's do SO3 and we'll do SO2 as our 2 examples of AX3 and AX2E. So we'll start out here. So we'll go SO3 will be our AX3 version. Okay. And what we'll do for AX2E is going to be SO2. Now these molecules both exist, and putting together the Lewis structure for these molecules is going to be what starts us on our ability to determine the shape or electron geometry and eventually the molecular shape. Now, one of the things that I'm going to get into a little bit less is going through every step of the process for doing the Lewis structure. Again, that's something you get more comfortable with tomorrow. You'll have an opportunity to do all these Lewis structures tomorrow in that dry lab. And so I'm going to give you the Lewis structures here, and then we'll give you the perspective drawing. But I'm not going to go through all of it every single time. Yeah, Maya.
Hello, good morning. Could the coefficient give us a hint on which steric number it is? You know, SO3, AX3, or is that just giving us an easy example?
If you know, yeah, so that's a really good question. If let me answer it kind of in this way. If you know the Lewis structure of one of the molecules, then understanding that it has 1 fewer bonded atom can help you determine that. But it doesn't specifically tell you one way or another what the shape is. The best way to do it is to just draw the Lewis structure in, and then you can start to really figure out all of the other things, like the number of lone pairs of electrons, number of bonded atoms, and that'll lead you to the VSEPR class and ultimately the shape. So yes and no, but it's hard to do that unless you actually know one of these 2 molecules.
Got it. Thank you.
So for SO3, there's our sulfur in the middle, our surrounding oxygen atoms. We actually have a total of 24 valence electrons here. And so the way we're going to actually draw this in, to draw the proper Lewis structure here, okay, is we're going to draw in all of our lone pairs of electrons and our bonds, knowing so sulfur is an atom that's in period 3 or below, so we can expand its octet, which is why it has in this example 12 valence electrons surrounding it, which is okay. You can expand its octet. So this is going to be your Lewis structure. We've got 1, 2, 3, 4, 5, 6, 7, 8, right? 8 on this one and 8 on this one, so it's a total of 24 valence electrons. And so what we do here is, if this is the Lewis structure, what we can do for the perspective drawing right? So these are all going to be, if we think about the oxygen as being, bonded to the central atom of the sulfur, what you have here is those oxygen atoms are going to try to get as far away from each other as they possibly can. In order for 3 things to get as far from each other as they can, they're going to actually remain in the same plane, but they're going to space out, if you will, along a circle that you could draw sort of in the plane of the screen or in the plane of the page. So the way we're going to do this, we're going to draw our, did not, come on. This is not working. Don't know why. And my pen is frozen. Well, that's not cool. I'm having some issues here for a second, so excuse me. There we go. That's better. There we go. My pen decided to stop working on me. And it's continuing to be funky. There we go. Here's our central atom of the sulfur. And what we're going to do is we're going to space our oxygens around as far as they can get from each other. Space them out all the way around. If you were to draw a circle around here, the way you'd space them out is you put them at 120-degree angles from each other. Right, you're essentially dividing that 360-degree circle by 3. Okay, so when you look at these bond angles, that'd be 120 degrees. This would be 120 degrees. And this would be 120 degrees. Okay, and so when you look at those, remember these are all the ideal bond angles here. If you have something other than oxygen at one of those positions, the size of that atom will actually have an effect on these bond angles also, right? The bigger the atom, the more space it takes up. And so we can look at an example of something like that in a minute, but that's going to be something I kind of want you to keep in your head, right? Remember, if all 3 of the atoms around that central atom are the same, they're going to all repel with the same amount of force against each other, if you will. If you have a bigger atom, that's going to repel more. And then in our other example here, we're looking at the AX2E molecule. A lone pair of electrons is also going to repel more. And so when we look at the SO2 molecule, if I just do the Lewis structure of that, we've got a sulfur, an oxygen, and an oxygen. Here we have a total of 18 valence electrons. And so with 18 valence electrons for the Lewis structure, right, we're going to have double bonds between the sulfur and the oxygens. Here's a total of 8 electrons on each oxygen, right? They each have an octet. The sulfur also has an octet, but we can expand its octet because if we have 8 electrons on each oxygen, that's only a total of 16. We have a total of 18 valence electrons here. So we're also going to have a lone pair of electrons on the sulfur. Is your hand still up or did you just raise it?
I gotta lower it, sorry, my bad.
Oh, okay, just checking. I just noticed it was up again. Here we go. All right. So in our Lewis structure, right, we have now, if we look at the sulfur, now we have bonds, right? So those are bonded atoms. But we also have this lone pair. And so in the perspective drawing, when we draw out a perspective drawing for this, okay, when we draw out a perspective drawing for this, what we could do here is draw again our sulfur in the middle and our 2 oxygens that are at about 120 degrees from each other. And then we have this lone pair of electrons up here. Now, you can feel free if you want to say, oh, that's in an orbital. Okay, don't worry about what orbital it's in. We're going to talk more about that in chapter 9. We're going to still draw our double bonds into our oxygen atoms. And what we're going to see here is that lone pair of electrons, okay, is going to affect the bond angles here, okay, or the bond angle. So there's only really one bond angle there. And what happens is that lone pair of electrons pushes more, pushes a lot on that bond. This lone pair of electrons pushes a lot on that bond. In fact, it pushes more than the bonds push against each other And the reason is really you don't have an atom out on the other end of this lone pair, right? There's no atom there to pull the electrons away from each other. So all the negative charge of the electrons in the lone pair are pushing with all of their force. Whereas the electrons in the bond, well, those are being pulled to some degree out toward the oxygen as well. And so what winds up happening is ideally you would have a 120-degree bond angle there, right? That's the ideal bond angle. But the actual bond angle will be a little bit less than 120 degrees because of how the lone pair pushes. Okay, and so that would be an example of where you would have the lone pair of electrons affects the shape of, or the bond angles, but also what you have here is a different shape also, right? This now, that particular molecule is no longer, so I actually haven't gotten into the shapes here, but this particular molecule, when we look at the electron geometry versus the shape, the electron geometry for both of these is going to be trigonal planar, okay? So let me go back over to our first one over here, right? So the electron geometry for anything, in fact, that's AX2 or AX3 that has steric number of 3, right? The electron geometry, right, or electron shape is going to be trigonal planar, okay, in the case of anything that's steric number 3. But if we have something where it's AX3, AX3 is going to have the shape of the molecule geometry or molecule shape. If you have a steric number 3 and they're all bonded atoms, that's going to be trigonal planar as well. Okay. And so for SO3, it's trigonal planar. If we look at the SO2 molecule, we're only, for the molecule shape, going to look at the atoms. Okay, and the molecule shape for SO2 is going to be bent, right? Because those atoms, they're oriented in such a way that they are, well, they're not oriented linearly. They're oriented in a way, it's like a bent line. So we say it's a bent shape. Okay. All right, so I want to do one more example in here just to illustrate another thing. So in the bond, with the bond angle examples there for SO2, right? That bond angle is less than 120 degrees because of how the lone pair of electrons pushes on those other bonds. Another example we could do, theoretically, you could make all kinds of molecules. And so one of the molecules sort of want to talk about theoretically is if you were to have something like BF2Cl, okay? Now this molecule would look something like this. So boron, Cl, F, F. And we put in lone pairs. Boron doesn't have to have a full octet, right? It's one of our exceptions, just like beryllium was. So you'd have a Lewis structure that looks something like this. Now, if you were to look at the perspective drawing of this, the boron in the middle, and the chlorine, I'm going to put that there, and the fluorine there, and the fluorine there. Something to think about is the chlorine is a much bigger atom than the fluorine, right? So it needs more space. And so if we were going to look at the bond angles on this, right, you could look at the bond angle between the chlorine and fluorine, right? And that's gonna because the chlorine needs more space, it's gonna push more on the fluorine atoms, right? And so this is gonna give you a bond angle that's greater than 120 degrees in both of those cases, right? The bond angle between the chlorine and the fluorine. And the bond angle between the two fluorine atoms, right? That bond angle is gonna be less than 120 because those are smaller atoms and they're not being pushed, they're not pushing on each other as much as the chlorine is pushing on them. Okay, so the size of the atoms is going to make a difference. Now, it's still going to be a trigonal planar electron geometry, but the shape or the molecule shape or the molecule geometry, instead of being just trigonal planar or bent, it's going to be sort of a distorted trigonal planar. Right? It's not perfect bond angles in this case, but they're pretty close. I mean, they're not super far off, but they do orient it in a sort of a pseudo trigonal planar geometry. They're just distorted a little bit from the ideal angles. Okay, so that takes care of steric number 3.
Professor, I actually do have a question about determining the angles.
Uh-huh.
So, for example, SO3, you have 3 oxygen molecules, so you would take 360 degrees and divide it by 3.
Mm-hmm.
That's with any of the AX3, AX2 molecules?
No, it's any of the, so any of the AX3 or AX2E molecules, if you look at their ideal bond angles, yeah, that'll be, you just say, hey, they're all going to lie in the same plane. Because it's not until you get to the 4th surrounding atom that they start to break away from that plane. Yeah.
Okay.
Yeah, if you look at the ideal bond angles, it's 120 degrees because yes, you're taking that circle and dividing it by the 3 bonds.
Okay, versus the exception you just talked about with the chlorine, but it's always about 360 divided by 3? Kind of.
Yeah, so remember, that's the ideal versus the actual, okay?
Got it, okay.
Yeah, so like the SO2, right? The ideal bond angle for SO2 is 120, but it's actually gonna be less than 120 degrees. All right. So the next class we have, make sure I have enough slides. Okay, the next class that we have is going to be steric number of 4. Now there are going to be, or next group is steric number of 4. Now there are going to be 3 different types. We're going to have AX4, AX3E, and AX2E2. And so if we look at a steric number of 4, I'm going to try to let these drawings speak for themselves as much as I possibly can, because this does start to get harder to depict. An example of an AX4 molecule would be something like methane. Okay, so methane would have a Lewis structure that looks something like this. But if I just take the Lewis structure and say, oh, that's showing me shape, it's really not, because this molecule isn't going to be planar such that all of the CH bonds are in the plane of the page. That would give us a 90-degree bond angle. In fact, it doesn't. What this actually gives us is a 109.5-degree bond angle. Okay, and you can look at it as all of the angles between all of the bonds are 109.5 degrees. However you want to draw them. Right? Of course, it's harder to draw this one, but there's a bond angle there, and there's a bond angle, if you will, back here as well, right? Those are all 109.5. And so when we draw this with perspective drawing, this is going to give us something that looks like this. Right? Where our wedges and dashes show atoms that are coming out of or projecting back into the plane of the page versus the lines which are in the plane of the page. So this is going to be an electron geometry. Right, that is tetrahedral. And it'll give us a molecule geometry, a molecule shape that's also tetrahedral. Okay, and so that's methane, and that's the AX4 class, right? This is AX4. But if we go and replace one of those bonded atoms with a lone pair of electrons, we get something like this. This would be an example or an example of this would be ammonia, NH3. And so if you look at the Lewis structure of ammonia, you'd have something that looks like this. Okay. And that Lewis structure, again, doesn't show you the shape, but if you were to draw out the actual perspective drawing, something like this would be a good way to do it. And hopefully you're seeing how this is mimicking the artist's rendering of these, just without needing quite the skill to render those in the same way. And so what you have here is you're going to have an electron geometry that's still tetrahedral. Okay, but now you're going to have a molecule shape that is called trigonal pyramidal. Okay, and rather than having 109.5 degree angles here, what you're getting is, well, as you can see from our actual image here, this lone pair of electrons has a larger repulsion. This is illustrated over on this right-hand side, right? So this has the lone pair has a larger repulsion, causing the angles to actually be more like 107.3 degrees, right? And so this trigonal pyramidal shape, it has the same electron geometry, but now it's a little different. Now, the difference between a tetrahedron and a trigonal pyramid is that if you have a tetrahedron, all 4 of the faces of that tetrahedron are the same size, okay? If you were actually looking at the trigonal pyramid as compared to a tetrahedron, what we're really looking at is sort of shape-wise is the shape that is between the atoms. Remember, it's not between the electron groups. So your actual shape is sort of this that I've kind of drawn in there, where the 3 sides, right, that are formed from the hydrogen, nitrogen, hydrogen face of this molecule, those are all 3 of those are the same size, but the face that's formed where the hydrogens are at the vertices, that face is going to be a different size triangle, right? And so that's a trigonal pyramidal molecule as opposed to a tetrahedral. They're not all the same size faces. And again, this is part of the reason why this becomes rather challenging, is you have to sort of be able to see some of these in your head, and these artist renderings should help you to do that, I would hope. Finally, in this class, we have the AX2E2 molecule, and an example of that is water. Okay, so water, when we've drawn it, well, you can draw it in a couple different ways, right? We've shown that this is a correct Lewis structure where we have the hydrogens that are opposite, directly opposite of each other in the Lewis structure. But remember, the Lewis structure doesn't show us the shape. And so in order to depict the shape, we need that perspective drawing. And we can draw this. I'm actually going to draw this out a couple ways just to try to make sure you can see how this looks. So the first way that I'm going to do this is I'm going to draw in my lone pairs of electrons in the plane of the screen, which means that my bonded hydrogens are going to need to be drawn using the wedges and dashes. Okay. Now, in this case, we have these lone pairs that are sitting in orbitals out here, and those are pushing on those hydrogen-oxygen bonds quite a bit. And so this angle here, right, is going to be less than 109.5. Try that again. Okay. Now I can draw this in a slightly different way. In fact, I could draw this putting the electron groups at any of the different vertices, but sometimes it's just easier to draw it such that it's like what we've done and used before. So the hydrogen there, got a lone pair of electrons over here and a lone pair of electrons over here. And if I draw it like that, I'm going to change my colors here so it's a little bit so you can kind of see what the difference is here. If I draw it like that, here's a wedge saying that that lone pair of electrons is coming out of the page at you. And here's the dashed line saying the lone pair of electrons is away from you. And so if we do it that way, then what we can do here is go and look at this bond angle there a little bit easier. And so that's less than 109.5 degrees. So it's more like 104. And so this has, again, a same electron geometry, right? The electron geometry is tetrahedral. But the shape, the molecule shape, the molecule geometry is bent. And that's because those lone pairs of electrons aren't included in the overall shape that of the molecule, right? We include those in the electron geometry, or the electron shape, as opposed to the molecule shape when we take into account water. And so that's what leads you to having a bent shape for water. And of course, that bent shape, now that we can kind of touch on this, right? When we think about the electronegativity arrows here, right? Those electronegativity arrows, right, are along those bonds, which are oriented with those bond angles. And if you take those and add those electronegativity arrows together, right, you get an overall electronegativity or a molecular dipole looking something like that. So that's where all that comes from with a water molecule. And so when we look at the bond angle here, right, that's more like 104 degrees. But what I expect out of you is just less than 109.5. I'm not asking you to memorize all those. Now, if you're a chemist, you should be starting to memorize some of these. But the key here is if you memorize the ideal bond angles and how those ideal bond angles are affected by either the atoms of different sizes or both things, right? Atoms of different sizes and lone pairs of electrons, you'll be in good shape, okay? And that takes care of steric number 4. Steric number 5, and so we're not going to get into in-depth examples of these. What I want you to see is when you have steric number 5, you have equatorial and axial atoms, okay? The axial atoms are going to be located right down at the bottom and the top of this linear axis that runs through the chlorine phosphorus chlorine bond. So this particular one is so PCl5 in this case. So we're not going to do all kinds of these, but we do have some examples in here. But you have chlorines that are both axial and then other chlorines that are going to be equatorial, right? So the chlorines that are circled in red are the equatorial chlorines, okay? Now, the way to look at this now is, well, if you have 5 atoms that are bonded to that central atom, in order to get as far away from each other as possible, they're going to spread out in this way. They're going to spread out so that you get 3 atoms around the middle that are 120 degrees apart, and on the top and bottom, you're going to get 2 more atoms. Now, when you look at these particular molecules, it's just the lowest energy. Now, you could, ideally, I would have a set of balloons, and you can show how they space apart by the balloons taking up space. Unfortunately, we can't do that, so we're left with the artist rendering here. But one of the keys here is, and it's going to lead to the different shapes of the steric number 5 group of molecules, is that you have these certain 90-degree repulsions. So if I look at the repulsion between an equatorial and an axial atom, let me change my pen is going crazy again. So one moment. There we go. Now it's coming back in. There we go. Okay. So what we'll do is I'm going to change my color here so it's just easier to see. So you have now these angles, right, between the equatorial and axial atoms that are 90 degrees. And you have that angle between all of those equatorial and axial atoms. And those are really, really rough repulsions. Those really repel each other a lot. And you have that between the upper and the lower, the upper chlorine and the equatorial atoms, and the lower chlorine and equatorial atoms. So essentially what you have there is these 6 90-degree repulsions. Okay, and then you're going to have repulsions between the equatorial atoms that are 120 degrees. So those repulsions, you really only have 3 of those, okay, in this particular molecule. Okay, now the 90-degree repulsions are the most repelling, if you will, right? The highest energy repulsions. So what winds up happening is when you start to replace the surrounding atoms with a lone pair of electrons, right? And so instead of having 5 surrounding atoms, when you replace one of those with a lone pair of electrons, as you can see right here, that lone pair of electrons, right, in there is actually going to want to go equatorial, because if you think about the repulsions that, let's say, an axial atom face, right, you would have 1, 2, 3, right, 90-degree repulsions for one axial atom. If you look at an equatorial atom like you see here, you're really only having these 2 90-degree repulsions, right? There's a 90 there and there's a 90 here. And those are the higher energy ones. These 120-degree repulsions are less of a problem. And so what winds up happening is the lone pairs go to the equatorial positions first. Okay. Now, the shapes that you get out of these are going to be, well, when you have just all of the surrounding atoms are the same, that is going to have a shape that is called, or an electron geometry that is, and actually for all of these, the electron geometry, right, is trigonal bipyramidal. Okay, it's 2 trigonal pyramids that are stuck on one on top of the other, right? So the shape of the, when they're all the same, the molecule shape of a trigonal bipyramidal electron geometry with all the surrounding, or all the electron groups are surrounding atoms, that's going to be also trigonal bipyramidal. But when you start to replace those surrounding atoms, you start to get new shapes. And so the molecule shapes, if you have an AX4E where you've replaced one of those lone pairs, is called the seesaw shape. And it's kind of a weird thing. I'm going to try to draw it out a little differently so that you can see where the seesaw shape comes from. Right, if you were to say, right, there's my seesaw shape. I don't know who came up with this idea, but somebody did. It's kind of amusing. And so if you were to say, hey, put this on the ground, right, and you have a little teeter-totter there, little seesaw. Right? And now, if you want to take that shape, you can see the, ooh, that's not the good color. 1 sec. Here we go. All right, you could say, oh, these can go up and down with each other, right? If you were to say, attach your 2 X's on the bottom there to the ground, right? It would teeter-totter, if you will. So that's where the seesaw shape comes from. And if you look at the bond angles there, when you have that lone pair of electrons here, right? That's going to cause the 120-degree bond angle back here, right? That's going to be less than 120 degrees. And it's going to cause the bond angles between the equatorial and axial positions to be less than 90 degrees because they're going to push those bonds away a little bit farther. Okay, so essentially any of these ideal bond angles pretty much become smaller when you replace lone pair of or replace one of the atoms with a lone pair of electrons. Okay, if you go to two lone pairs of electrons, you have a T-shaped molecule. So your T is right here, and again these angles here, right there and there, those are going to be less than 90 degrees, less than 90 degrees. And so that's going to give you something T-shaped. If you replace three bonded atoms with lone pairs, all three of those lone pairs are going to go in the equatorial position, okay? And so what that leads you with is something that's linear, and that one will have a 180-degree angle. That's just going to be 180 degrees between those two bonds, okay? And so that's what you'll see there, because now you have all the repulsions are the same around that equatorial plane, and so they're going to repel the same amount, which is just going to make all of those atoms in a line. Okay, so those are the different shapes that you get if you have a steric number of 5, and but they're all the same electron geometry, trigonal bipyramidal electron geometry. Okay. And so you can see some more about the repulsions and how the repulsions affect the actual angles here. So if you look at, say, the angle between axial and axial atoms in this particular molecule, so this one is sulfur tetrafluoride, right? You can see that because this lone pair of electrons pushes more, the actual bond angle is less than 180 degrees between axial and axial. And it's also going to be less than 90 degrees between the axial and equatorial. And then if you look at that angle between neighboring equatorial positions, right, that's 101.5, so that's significantly less than 120 degrees. The same thing goes when you now replace two of those two of those atoms with lone pairs of electrons for something like chlorine trifluoride. Now you have a much smaller, again, the bond angle that's less than 90 degrees. So in both of those cases, you're getting a reduced bond angle in basically all these cases when you have that lone pair of electrons in the repulsion, right? So when you compare the actual to ideal, when I'm asking you for an actual bond angle, you should know that basically, is the bond angle going to be larger or smaller than the ideal bond angle? And that's going to be determined by if it's a lone pair of electrons that's pushing it away, or maybe a smaller or larger atom that's pushing away those bonds. And finally, when we look at steric number 6, steric number 6 is going to have an electron geometry that is called octahedral. Right, so octahedral electron geometries come about when you have 6 electron groups. And you might be saying to yourself, well, how is 6 and octahedral, how did that go together? Well, when we look at the actual molecules here, the shapes that we're looking at are based on the faces of the shape that's created, assuming that each of the atoms, of the surrounding atoms, or the central atom in the case of something that's trigonal pyramidal, it's assuming that you have atoms at each of the vertices and you make faces for the shape, okay? So if you have an octahedral molecule, you get that octahedral molecule because you have 6 vertices in this particular shape. So the molecule we have here has a triangular face here, right? A triangular face here, right? One on the backside there, another one on the backside there, and those are all on top, and you get the mirror image of that on the bottom. So you have 4 faces on the top and another 4 faces on the bottom, okay? That's where the octahedral shape comes from. Just like the tetrahedral shape is based on the faces all being of the same size, okay? Now, when you have something octahedral, something like sulfur hexafluoride would be an example of that. So one of my favorites, right? They're all going to space out such that you have 90-degree bond angles. I have this picture here. Okay. So you're going to have 90-degree bond angles between all of the bonds there. Okay, whether they're, and so there's no equatorial and axial when you have something octahedral. They're all equivalent positions. No matter how you rotate this molecule around, all of the positions in an octahedral molecule are equivalent to each other. Okay. When you replace one of those atoms, right, with a lone pair of electrons, then of course your lone pair repels more. Right, you have a greater repulsion. Okay, and so the bond angles here, which would usually be 90 degrees, those are going to be less than 90 degrees. Okay. Now again, you can get this information from the Lewis structures, right? And then apply that when doing the perspective drawing. Okay, so if you were to do a perspective drawing of something like AX6, something like sulfur hexafluoride, right? The way you do that, you'd have your sulfur in the middle. You could do it a couple of different ways. You do it like this, or use the wedge and dash for 2 of the fluorines, which kind of in a little bit mimics the picture that's up there. Or you could also do it such that you have just 2 fluorines that are in the plane of the screen or the page, and you have on one side one going out, one going back, and on the other side one going out, one going back. And so again, it's going to take probably a little bit of practice drawing these and being able to picture these shapes in your head, but the difference between those 2 shapes, right, the difference between there and there is a 45-degree rotation, right? That's really all that difference is, right? You're just taking the molecule and you're turning it 45 degrees. And so you take these fluorines that are sort of in the page and you're turning them this way. And when you turn those this way, you bring these other ones that were in and out of the page, right? And you're turning them that way, okay? And so that's what you get when you go between those 2 shapes. And so again, it's going to be important. Now, one of the ways that you might mimic these is take some pens, right? And you can say, oh, here's my octahedral molecule, right? Where there's atoms, surrounding atoms at the vertices or at the ends of the pens. And so you can start to see them in this way, right? Where are those atoms with respect to each other, right? Again, balloons, if you have 6 balloons, tie them all together in the center and see the shape that's made. It's kind of the Willy Wonka's everlasting gobstopper shape almost in a certain sense. But anyway, you've got this steric number 6 has, again, 6 vertices. And when you start replacing those electron groups, you start to get bond angles that are smaller. When you replace the second electron group, though, something that you get with the second electron group is that the electron groups want to be as far from each other as they possibly can be. So you'll get one opposite the other, right? Again, these electron groups, they repel more, so they want to get farther away from each other. Right? If you put the third one on, it doesn't matter where the third one goes. The first 2 are going to be opposite. The third one can be at any of those positions. And when you get the fourth one, if you were to have the fourth one, it would be in that 4th position. So those are the basic shapes that you get there. And each time the bond angles are going to be influenced by the positions of those lone pairs. So when it comes to these shapes and electronegativities and dipole moments, so when you think about these, the dipole moments of molecules, you're taking now the shapes, and you have to take the electronegativity differences in the bonds together to determine whether that molecule is going to be polar. Now, in the examples here, note these arrows here, I'm just going to point this out, they're pointing the wrong direction because, at least for chemistry, those are, it's a different type of arrow, okay? So the arrows that we should actually have, you guys know how to do electronegativity differences right now. Those arrows are based on the physics interpretation of a dipole, which is different from the electronegativity arrows represented by chemistry, okay? Stick with what we've done as far as electronegativity arrows. Just know that they're opposite. In physics, they're pointing in the direction of the magnetic pole, right? In chemistry, we're pointing it in the direction toward the more electronegative atom, because we're more interested in chemistry and where are those electrons going rather than what is the magnetic pole. And so I apologize for that as part of the slide. It's something that I'm going to change as soon as I get new images, because it's kind of mind-blowing that this isn't a chemistry book in some cases. But anyway, you can take those electronegativity differences and start to apply that to determine whether a molecule is going to have a net dipole or not. And it's just going to be based on your ability to draw these and see these perspective drawings and understand the electronegativity differences between the atoms, okay? It's fairly simple. Look, we've talked about it for water. You can expand that to other substances as well, okay? That really takes us to the end of chapter 8. What you're going to get to do tomorrow, though, in the lab tomorrow, so after we talk, we're going to open up chapter 9 and start talking about chapter 9 a little bit, and then you're going to start in on the Lewis structure lab. You're going to get lots and lots of practice with this stuff. So you'll be able to start to draw out. Remember, drawing out the Lewis structure and then drawing out the perspective drawing is of utmost importance when you're trying to do the shapes in VSEPR theory. Okay? And with that, we will end our lecture for today there. Yeah, should be good for the day.